Okay, let's get started. So today I'll just do one of your homework questions because I figure like, I don't think he went over Zorn's lemma. And like I think one of your homework questions had like Zorn lemma, right? So like unless you all know how to do that. But I think it was proving every ideal belongs in the maximal one. So do you all remember that? Or I think it was the last question on your homework. Yeah, so after that, I will go over finite fields. I mean, you don't have any homework on, I mean, not like, properties of finite fields, but, just important facts about it. And then after that, I'll leave it up to all of you. Yeah, we could probably do other homework questions if you like. I mean, or we could do like final review. But like, I feel for final review, I think he's like posting solutions anyway, right? So, okay. So a partial ordering, on a set S is given by relation. So this is just notation, right? It's not less than, there's just a notation for certain ordered pairs of elements in S such that, so one, A is, but if you think of it as less than or equal to, this is obvious, right? You're always less than or equal to, yourself. And two, if A is less than or equal to B is less than or equal to A, then A equals B, yeah? Then they are the same element. So this is, they call it anti-symmetric law. This is just a name. And three, if you have transitive property, right? If A is less than or equal to B, B less than or equal to C, then A is less than or equal to C, right? So this is called transitive law. So no, this is partial ordering, yeah? So by partial, it just means, if they are related, then it must satisfy, 1, 2, 3, right? It's not true every element is related to one another, right? So one example of that is if I just take S to be the set of all subsets of R, right? Not every, and then we define less than to be the subset, yeah? Then not every set can be compared, right? Because like, for example, the set 1, 2, 3 and 2, 3, 4, like it's not true that there is like this is not true, right? That one is contained in the other, right? It's not true here, right? And it's, so these can't really be compared, right? Because like they're not necessarily subsets of each other. Yeah, does everyone see that? So that's what we mean by partial ordering. So but some of them could be compared, right? Like 1, 2 is less than or equal to. So in this case, is a subset of 1, 2, 3. Yeah, and you could check that, 1, a set is always a subset of itself. 2, if you have T is a subset of T prime is a subset of T, then T prime equals T. Hopefully that's obvious. And 3 is also obvious, right? If you're a subset of T prime is a subset of T double prime, then T is a subset of T double prime. Yeah. So the important thing to note is, from here, not every 2 elements are comparable. Right, so in this case, my elements are sets, right? Because S is like the set of subsets. So, everyone clear on this? Yes. Does everyone follow? Okay. So now, what does it mean to be a chain? So so the second thing, a subset T of a partially ordered set S is a chain if every 2 elements A and B in T are comparable. Yeah. So it's a subset, right? Because not everything can be compared, but if we take a subset of those, it's possible that all of them could be compared, right? So i.e., for any 2 elements, A is less than or equal to B less than or equal to A, or both. Yeah. If it's both, then it just means they're equal. And definition, we say U and S is upper bound for a subset A of, is everyone okay if I write POS for partially ordered set? Yeah? Is everyone good with that? It's faster. Okay. So POS stands for partially ordered set. S if A is less than or equal to U for all A and A. Yeah? And we say finally that this is sort of what we want in our homework question. An element POS of a partially ordered set S is maximal if there is no S in S such that U is less than S. Yeah. Everyone clear on this? I mean, that makes sense, right? Maximal. So no, again, let me just say maximal is not maximum, right? Maximum, maximum sort of means you're bigger than everything, right? But that doesn't really make sense here, right? Because not everything can be compared, right? If I tell you I'm bigger than everything, then it's sort of like under the assumption you can compare with everything, right? So, but here, not everything can be compared, right? So think of maximal as, it's the it's like the biggest amongst those that compare to it. So how about that? Is everyone good with this? So Zorn's lemma. So this is what we'll use. Yeah. If S is partially, I don't know why I wrote that again. POS, such that every chain in S, right, has an upper bound. in S, then S has at least one maximal element. So you sort of see, maximal element. Yeah, definitely. So with that in mind, so you sort of see like why we need Zorn's lemma for the homework question, right? Because Zorn's lemma basically says we have a maximal element, and in this case, if you think of it, our element would be like an ideal. Yeah. So let's do our homework question, right? Our homework question says every proper ideal I is contained in the maximal one. Yeah, is that true? Is that what the question asks? If it's not proper, then it's the whole ring and it's contained in itself. Yeah, the whole ring is clearly the biggest. Yeah. Actually, I take it back. If it's the whole ring, it can't be true because I don't think they define maximal. I think they define maximal as it has to be proper. So anyhow, so what's the idea here? So we're gonna let R be ring, and I don't want to use I. Let's let N be an ideal. Be an ideal of of proper ideal of R. Then so i.e. N is not R. Then we're gonna denote S to be the set of ideals A containing ideals A that contain N. Yeah, so such that we contain N, and A is proper ideal of R. Does everyone understand why I need proper? Yeah, because if I didn't, then the whole ring R certainly contains N, right? And that's certainly in a sense maximal under this definition. Yeah, and we don't want that, right? Because our definition of maximal ideal is proper ideals. So okay, so does everyone agree if S has maximal element, we are done? We are done. Because by definition, the element, if you belong in S, you contain the ideal N. And by this definition of maximal, there's nothing that contains it. There's nothing bigger that contains it. So is everyone clear on this? So if S had a maximal element, we are done. Everyone follow. I need you to follow this because we're basically going to prove it's it has a maximal element by. So how do we show it has a maximal element? Well, Zorn's lemma. Yeah. So we are going to define S is POS, right? Let's make it partially ordered by saying A is less than or equal to A prime if and only if A is a subset of A prime. Yeah. So with this, we define this to be our partial ordering, and this makes S into a partial ordered set. Yeah. So from here, right, since S is a POS now, we need to show every chain in S has an upper bound in S. Yeah. So once we do that by Zorn's lemma, we are done. We have a maximal element. So let's move on. So let's let T No, yes. I'm saying like I already checked before that subset is a partial order. So I mean, you would have to write that, but yeah. So let T be a chain. Just check it satisfies those three properties, right? Is a chain in S, so everything can be compared, yeah. So in other words, so T contains all ideals. I don't want to say all. Contains ideals. Of course, these ideals, you're in S, right? So these ideals contain the original by definition. Ideals that all can be compared. Yeah. If you remember the definition of chain. So what do I need to show? I need to show it has an upper bound. Yeah. Everyone follow from Zorn's lemma? I need to show this chain has an upper bound. So what is your suggestion for the upper bound? If I have a set of ideals, what new set can I make that includes all the ideals? What operation can I do? Union, good, exactly. So I could let I be index set. Let capital I be index set. So because T could be infinite, right? So so we're gonna let I for I and I be the ideals of T. So the reason we put index set is because we don't know because infinite could be many different types of infinite, right? Like it could be something I can't write out. Like for example, if it was like the integers, then I could write it out as this, right? I equals 1 to infinity, right? So this is like, it's infinite. It's like integers, right? 1, 2, I1, I2, I3, I4. But what if it's infinite, like the real numbers, right? So like, I can't write that out, right? So we just let, I denote an index, and then we just, write I and I. Okay. So this I and I be the ideals. So these are ideals of T. Not in T, sorry, not of T. T is not a ring, it's a chain. So from here, the idea is consider union II, yeah? I and I. So let me just say, if this was an S, does everyone agree this is upper bound? For T. Use from the definition of upper bound. We are an upper bound if we are bigger than or equal to, in this case, we can, bigger than is contain, right? Because it's subset. If we are bigger than or equal to every element in T. So we contain every ideal in T. Okay, good. So, but we need to show it's an element of S, right? That's the thing. And S in our case is an ideal that contains N, right? It's a proper ideal that contains N, right? So I mean the fact it's proper is clear because how do I say this? The the fact that, let me think. Yeah, so really the only thing you need to check is, well, I I just need to check that it's an ideal. That's really the first part, right? So in general, it's not an ideal. The union of ideals is, huh? This element is not in the chain, right? I mean, T is my chain. I mean, we're considering the union need not be. Yeah, you need to prove it's an ideal, right? So, like in general, in general, if it's arbitrary, union I and I is not ideal. So here's why, right? Because if I let A, B be in union, right? We could even make it like finite, right? But A is in some I, let's call it, we could just call it I1, yeah. I1, and B is in some I2, right? Then is it true that A plus B is in the union? Not necessarily, right? Because I don't know how these two interact. They belong to two different ideals, right? Does everyone see this? Yes or no? Like this need not be the case, right? So, but what saves us is that we have a chain. Everything can be compared. So in general, this doesn't work, but let's do the proof that it's an ideal in our situation. So let AB be in the union. Then A is in IM for some M and B is in IN, right? Since this is a chain without loss of general, like one of it, they have to be comparable, right? So without loss of general, let's say IM is a subset of IN. Then AB, right, belong to IN. Do you all agree with this? So here, this is because T is a chain, right? Everything can be compared here. You all follow? Is there something you're confused with, Jacqueline? So we're proving the union is an ideal in this case, right? Because S is the set of ideals that contain your end. So we need to show this union thing is an ideal. So, right? Because upper bound by definition has to be an element in S. Okay, so do you all agree, like up to here? I need you all to follow because it's important that we're using the fact T is a chain, or else, like I said here, like it's not true in general that the union of ideals is an ideal. That's just incorrect. So does everyone follow up to here? So AB belongs to IN. Okay, now it's easy, right? Now A plus B, well, A plus B is an IN as IN is an ideal, right? So, but if I belong to one element, I belong to the union, right? So, whoa. So A plus B is in the union I and I, right? Because what does it mean to belong to the union? It means I belong to at least one element of the union, right? So, and I belong to IN. If that's clear, right? I mean, if you don't like this index, right? If I had like S1 union S2 union S3, what does it mean for like A to be in here? It means A is in like SI for some I, right? It doesn't have to be in all of them, right? If it's in all of them, then you're in the intersection, right? To be in the union, you just need to be in one of them, right? So so if A was in S1, then I'm in the union. Yeah. And then similarly, it's the same idea for all the other properties of ideal. Yeah, you just use the fact it's comparable, uh, and then use the fact that the bigger one is in the ideal, is an ideal. So example, right? Let, and I mean the magnet property is easy, right? Let A be in the union, I and I. So A is in IN for some n, right? Then RA is in IN, right? As IN is ideal. So if I'm in one of them, I'm in all of them, right? I'm not in all of them. I'm in the union. Yeah. So that sort of proves the magnet property, right? Of course, R is in my ring. Uh-huh. Is everyone clear on this? Yeah. So this is indeed an upper bound, right? Because we certainly contain, union I and I certainly contains I for all I. Yeah, so we're certainly in an upper bound. And this was an arbitrary chain, right? I didn't choose T. T was just some arbitrary chain. And then I denoted I's to be the elements in it. So you see by Zorn's, right? Like we have a maximal element. And you're pretty much done. Okay. Yeah, the saving grace here is really we have a chain. Yeah. So we could show in this case the union is actually an ideal. Why is it proper? So let me think. Uh-huh. So I think that's Cartesian. There's the Cartesian thing, right? If let me think. So oh, you're right. I didn't show it's proper. Oh, okay. So so I think this also uses the fact it's a chain. So let me try to prove it. I didn't think of this. So suppose union I and I equals R. Yeah. Then for all R, then let R be an arbitrary element. Let me see. And let R be an R. Then R is in the union. So R is in is this what I want to do? So R is in IN for some N. Yeah. So I think we need to use the fact that yes. It's I need to get a contradiction somehow. And I need to use the fact it can be compared. Everything can be compared. So if, how about this? Yeah, I need to. Yeah, you need to do that. That's certainly necessary because yeah, I think it's, yeah, did not think of this. So if I had something like this, right? Why is it the case that uh oh, I see. It's like a chain argument. Um so I think what I want to do is say let R how about this? Let R be an let R be an arbitrary element in R. So I need to show that, there is one thing that isn't in all the others, right? So what I want to say is, well, so what I sort of want to say is if R isn't in, since all of them can be sort of like compared, like in a sense, like the union is pretty much like sort of like I infinity or something. um I don't want to say this. Okay, I have not thought of this yet, so I will. How about I email you all? When I don't want to waste time. Uh, but yeah. But you certainly need to show it's proper. But I think it's from the fact that like, you know, because if there's like there's sort of like an I infinity, yeah, and that thing is like proper because like this one is also an element of T or something, but mm, yeah, okay. Okay, with that being said, are there any homework questions or like final review questions you want me to go over? I checked the final review. I think like really the only surprising thing was the companion matrix. But all right. Yeah, so finite fields, if you really want me to go over it, so the point is, I'll just go really quick. If E is a finite field of characteristic P, then E contains exactly P to the n elements, yeah? For some n. So every field of characteristic P is some power of P, right? And it turns out that, if I fix an algebraic closure, ZP, yeah, I could describe the roots. So this is Z mod PZ, yeah. Then the elements of E are roots of x to the p to the n minus x. Yeah. So this is fairly easy, right? So if I consider the multiplicative group, right? E cross under multiply. How many elements does this have? If E is finite field of P to the n, finite field with P to the n elements, how many elements does the multiplicative group have? So, P to the n minus 1, right? And this forms a group, right? So it's minus 1 because I take out 0, right? And you know that given group G, right, and A and G, A to the order of the group is identity, right? Do you all remember this? This was a consequence of Lagrange theorem. So similarly here, given A and E cross, right? Basically E without 0. A to the P to the n minus 1. In this case, what is E? If it's under multiplication, the identity is 1, right? So A is a root of x to the P to the n minus 1 equals 0. Oh, sorry, since I already wrote root. It's a root of this thing, right? And that's pretty much it, because if we add in 0, right, i.e. this thing, if I factor it out, it's x to the P to the n minus 1. Yeah. So this is the root of 0. This is all the non-zero elements. Yeah. Does everyone agree or follow? I can't really how to say it. I mean, if I don't fix an algebraic closure, I can't really say the elements of how do I say this? Because the roots, right? It's because a priori, right? I'm defining a map from, how do I say this? Like, to say they are zeros, so to say roots, right? It means they are algebraic elements, right? And without stating an algebraic closure, it's just like up to isomorphism, right? There was no issue with Q because we sort of know what the algebraic closure of Q is. I mean, we know it's like a subset of C, and we know how all elements there look like. We have like names for them, right? We call it like I and like root 2, but I mean, like, we don't really have names for like the algebraic closure of like a finite field, right? if I told you, like the most, for example, like x squared plus x plus 1, for example, if I mod this out, right, the most you could say is this is z mod 2z adjoint alpha, right, where alpha is a root of this, right? We don't really have a name for alpha, as opposed to like, q of x quotient out x squared minus 2. We have like, we have like we have a name for this because we stated the algebraic closure as a subset of C, the complex numbers, so we could actually write what this is. But here, like, it's like a pedantic thing, but if we don't fix an algebraic closure, we can't really say, what this alpha is. Yeah. Okay. So from here, right? And so we note that if you remember, for finite fields, this group, right, E cross under multiply is cyclic, right? So you see that it's E for any finite field extension, it's always F adjoint alpha, right? Where F is like Z mod PZ, if you like. We are always adjoining one element. It's always a simple extension. Yeah. So this is if from here, right? Here I assumed there is finite field of p to the n elements, right? And then I said, oh, then it must satisfy these properties, right? But how do you know a finite field of p to the n elements exists, right? So we can actually define it this way. Normally, we would have to quotient out by irreducibles, right? That's very annoying, right? Like, how do you know root 2 exists? Well, because we constructed the field, you know, by modding out by x squared minus 2. Well, there's an easier way for finite fields, and it's based on this, right? This thing has no double root, yeah? Or like has no root with higher multiplicity. So the way you check this is the derivative is non-zero, right? The derivative is never zero because the derivative is this. And this is -1, right? We're in characteristic P. So since it's non-zero, we don't really have, all the roots here are distinct. Yeah. Just so you all see this, right? If f of x had a double root, the derivative would also have a root, right? Like, I mean, this is just, you know, right? So if I plugged in 1, right, f prime of 1 would also be a 0, right? But you see here, f prime of whatever is never 0. So all roots are distinct, right? So these are all distinct elements. So what we're going to do is we're going to let K be subset of, the algebraic closure, just because we fixed it. Subset of ZP bar with the roots of x to the p to the n minus x. Yeah. So this is just the set of the, the set where the elements are the roots of this polynomial. Yeah. And then basically we show it, the book shows it's a field. Yeah. So no need to quotient out by anything. No need to do anything. Just let K be the set of these roots and then show that it's a field. So it turns out that, fields of order p to the n always exist. Is everyone clear so far? So, I mean, I think that's what your professor went up to, right? I mean, and in showing it's a field, right, on Wednesday, you had to show sums was, sums belong to, but like you're just using property that this is true, right? And like a to the p, b to the p is ab to the p, which is ab. Something like that, yeah. Like just these weird properties to show it's a field. Is everyone good on this? So I was going to talk about the final review. There was one question. I don't know if you're expected to know that. Like, I looked at that one. Like, do you remember if on the final review it asked like companion matrix and like stuff like that? how can an element be a finite, like, so how about this? Z mod 2z, like the one I just wrote. If you believe me that this is irreducible, right? Then this is Z mod 2z adjoint alpha, right? So this is the set of A plus B alpha, where AB is in Z mod 2z. Can one generate this? Can you get, there's no way you're gonna get alpha just by adding ones, right? Because this is generated by 1 and alpha, not just by 1. So but yeah, the final review, okay, and by the way, this is the field of 4 elements, right? 2 squared, so it's 4. So but there was one thing with companion matrix. Do you want me to go over that, or like, because I realize it's not part of this course. I think that's like, that question is like 121B or something. I don't know why he's asking it here, but like, like stuff with like minimal polynomials and stuff. Yeah, like or I mean, if you're taking 121B, you probably know how to do it, but like, do you want me to go over that real quick, or at least how to get the matrix? Because I have a feeling people don't know linear algebra, so it's actually not that bad. Like, if matrix for multiplication by alpha, right? By alpha. Okay. So with with basis 1 alpha to the n minus 1, right? And alpha, the min polynomial, the irreducible polynomial of alpha, we called this, it was a naught plus a1 alpha plus the dot plus a n minus 1 alpha to the n minus 1 plus alpha to the n, right? This was 0, right? So agree? Like, I'm just making, the the irreducible polynomial is some degree, let's just say it's n, right? Then your basis is from here to n minus 1, right? Because you can express any n power or higher in terms of the n minus 1 powers and lower, right? Everyone clear on this? So no. So the irreducible polynomial is, so alpha is a root of this thing, right? So when I plug in alpha to the irreducible poly. Okay. So this is easy, because if I just let the rows denote, like, this denote the coefficient for 1, coefficient for alpha squared, then it's easy, right? You just look at what multiplication does to each element. So if I multiply by alpha to 1, what do I get? What is 1 times alpha? So what is 1 times alpha? Okay, and let's read it out, right? This is 0 plus 1 times alpha plus 0 times alpha squared. If I rewrite it in terms of my basis, it's this, right? So this is 0, 1, 0, 0, 0, 0, 0, right? That should be the first column of your matrix if you look at your final review. Same thing here. This is alpha squared, which is 0 plus 0 times alpha plus 1 times alpha squared plus 0 times alpha to the n minus 1. So this should be 0, 0, 1, 0, 0, 0. Do you all see this? So this should be like the first column of that matrix they have. This should be the second one, right? Do you follow? Or, okay. Now it gets interesting here, because this is alpha to the n. But what's alpha to the n? If you look here, this is negative A naught minus A1 alpha minus a dot minus AN minus 1 alpha to the N minus 1, right? So the coefficient, so it should look like this, right? And that should be the last column of your matrix. So yeah, so this is just linear algebra. And then the other questions are just like 121B questions. It's like asking for like min poly and stuff. But at least you know now how to get the matrix. I mean, as for the Zorn's thing, I feel like since he didn't go over it, like I don't think you need to worry about it. I mean, it's just for the homework. I mean, but yeah. Uh, what? Well, what are the zeros of this? It's, if you remember, it's e to the 2 pi I k over 28, right? Something like that. Yeah. I mean, this is certainly cyclic, right? It's generated by what I just wrote. I mean, an easier example is this, right? This is generated by e to the 2 pi I over 3, right? So it's the elements, it's certainly, you know, the elements are this, right? It's e to the 4 pi I over 3, and 6 pi over 3, e to the 6 pi I over 3 is e to the 2 pi I, and that's just 1, right? If you want, you could write this as, yeah. It's just the unit circle. Yeah, yeah, Jacqueline, I think it is quite a lot. I don't know. But I feel like sometimes I don't think he spent time on this review, right? Because I remember reading like one of the questions asked you to show something's integral, and then like 3 questions later he defines what integral means. So like I was like, shouldn't you define what integral means before asking someone like what to show something's integral? But like, yeah, I don't think he really looked over it. But yeah, the final review certainly like looks long and scary. That's for sure. And you have like what, like 2 hours to do it? Yeah. Yeah, I feel like, I don't know, like you all did well on like the quizzes and stuff, right? I mean, and like the previous midterms. No. So he made the midterm. So chances are it'll be similar to the midterm. Yeah. So the free response question for quizzes, it's made by me and the other TA. So if you look at the difficulty of the midterm, then that's sort of a good judgment of like, how hard the final will be maybe. I do find that I don't know if he really looked over the homework questions because, he assigned Zorn's lemma and he didn't go over Zorn's lemma. So like that was kind of awkward when I when I first looked at it. I was like, he didn't even go over this. Like, let me see. So he'll give stuff he went over in lecture, but like lecture is just him going over the book, right? Oh, 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 sorry, Joe, are you still here? It's proper because I'm dumb. So like they if like all of them don't, because since they're all proper, they don't contain one, right? So like because if your ideal contained one, it would be the whole ring, right? So all the ideals cannot contain one, right? So like yeah, then yeah, so their union wouldn't contain one either. Okay. Uh is that all? So if you have any questions, last minute, you could email me. I mean, I check my email pretty often. So yeah. Other than that, it was fun. I think I remember some of you. I think Jacqueline, you were in my like what 180 or something, and then I'm not sure if I had you, Joe or Joy before, but I certainly remember Frank. Yeah, it was pretty fun. Okay, yeah. Anyways, good luck. I will.